So I'm working in a group of Jan Simon. So he's my boss. So I'm a postdoc at his institute. And I'd like to stress, so I'm not presenting my own work, but mostly that of my colleague Nadia. So he's working on paper mechanics, and Tian Cheng, who's doing the thermoplastic part. So let's jump right in with a concept of external operators in FEniCS. So let's do a flash survey. Who has used external operators so far? Usual suspects, I guess. You haven't? No? Okay. Okay, but not too many people. So and let me explain you a word or two about that. So the unified form language is awesome if you want to express something that you can express as an integral. Yeah, any variational forms that you like, which does not hold if you're going to inelasticity. So like viscoelasticity, plasticity, damage phenomena. So you have those constitutive flows typically have branching, you have branching conditions, you have local Newton iterations, you have history variables, and you cannot properly do that in UFL. To show you some examples of that material behavior, so here on top we have some so this is a stretch curve in that sense of PA6, so nylon. We have a very small elastic regime. Then you have a viscoelastic regime, so you can already see some hysteresis in there. And then you get severe plastic deformations going up to a stretch of 1.2, so definitely finite deformations. Same holds for, in this case, it's an example uniaxial tension in a paperboard sample where you get severe damage and damage localization with that. So everything, so all that material behavior cannot be properly expressed in UFL. And luckily, there's a solution for that in FEniCS. It's called external operators, which extend the uniform form language by arbitrary code that you like. So so we are doing it in Python using JAX. So in order to use automatic differentiation, which is really nice. But I learned you can basically do anything like C, Numba, even if in Python, so anything you can call from, even Fortran. So if some legacy code flying around, anything that you can call from Python. So then the rest is basically unchanged, your assembly, and you can use whatever material model you like. Nevertheless, there's a catch with finite deformations there, so finite inelasticity. The problem is that you typically do a decomposition of your deformation gradient tensor into elastic and inelastic parts. Yeah, multiplicative decomposition. And this decomposition is not unique, so you can insert any rotation matrices, any orthogonal tensors, and to come up with a different decomposition of F, which has the disadvantage that also derivatives with respect to your right Cauchy-Green tensor are not unique, and that's typically what we need in solid mechanics. I mean, we start with our Clausius-Duhem or Clausius-Planck inequality if we want to be thermodynamic consistent and derive the stress. If we use the Helmholtz free energy, derive it with respect to some C. Yeah, and also for plastic rates, accumulative plastic strain, so all derivatives that are turning up there. Now what we do is we formulate everything in what we call co-rotated intermediate configuration, yeah, which you can interpret as an orthogonal pullback, although also we could assume it's a push forward from the reference configuration and delivers you a different elastic, so different Cauchy-Green tensor, elastic Cauchy-Green tensor. And this one has the advantage to be unique and symmetric. So then we can formulate all our potentials in this co-rotated intermediate configuration and use automatic differentiation directly, which otherwise would be ambiguous to do. Yeah, so this really solves the problem that you face with AD, and we want to be using automatic differentiation. I mean, whoever has been dealing with this, if you are deriving all these quantities on your own, I mean, then this is just the first derivative, then you need a second derivative for your tangent modulus, and depending on the complexity of your material model, you will end up with pages of tensor derivations, so this is no fun, yeah, so AD really does the trick for us there. Now, how does this work? So typically we start with some mesh kinematics boundary conditions, your typical input. We write our material routine in JAX then, so everything you can think of, return mapping algorithm for plasticity, time integration, local Newton iterations, wrap everything as an external operator using this library or module, and then vectorize across all Gauss points using JAX VMAP. And we have only done this for the thermoplastics case yet, then also use CUDA in order to exploit GPU parallelization. So 2 examples that I brought. One is paperboard, so not your typical engineering material, but widely used in the packaging industry, and we are cooperating with some packaging producer. What you typically do, I mean, it's not pure paperboard. Typically, you have some polyethylene, aluminum foils laminated with a paper. But this is already a severe challenge. And then you do creasing, folding. So essentially, the stuff you did at school or earlier when you were building paper planes. Yeah. So you induce plastic deformations in the material in order to have a well-defined fold. Earring.
Folding earring. What is earring?
Earring is a that's a result. So if you have folded it across several directions, yeah, you get some warpage in there, some distortions, and this goes on the earring.
And this is called earring.
Yeah, that's what I learned from. I'm not going into detail with what specific deformation patterns you have there. Yeah, so creasing and folding are the most important parts for us right now. Okay, so in paper, I mean the way it's produced, you get a severe anisotropy. So paper fibers, cellulose fibers are aligned in the machine direction. You have a cross direction, and then certainly you have a vertical direction, and you induce those plastic deformations, particularly in Z direction. That's what you want to get. And now we treat the in-plane and the out-of-plane behavior differently here. The out-of-plane behavior, therefore, we need this multiplicative split. We formulate our Helmholtz free energy, our yield surface, and so on. And so this is just a qualitative example here of a compression in out-of-plane direction. Second example, thermoplastics. So in this case, the figures show so-called thermoplastic sheets are reinforced with carbon fiber, which are heavily used in industry to rapidly produce parts. So we are just dealing with a matrix material, the thermoplastics, where we have a viscoelastic molecular network resistance and a viscoelastic and viscoelastoplastic intermolecular resistance, all in finite deformations. It's temperature dependent. The chi is the crystallinity, so semi-crystalline polymers, so they have some amorphous and crystalline regions which change upon deformation, temperature. We do not couple that yet, yeah, but it's so far it's just in one way coupled by the crystallinity, and then we if you load it, you get those curves showing some severe, in that case, plastic localization. So it's in here, this is a notched dog bone specimen. You really pull this apart a lot. So in here, the deformations are not in the like 20%, but way higher. And this is really stable and working nicely then. In order to compare this with experiments, so from exactly this example, we used some DIC measurements, which a former colleague of mine did, in order to compare, in this case, the local strain patterns here in horizontal and there in vertical direction, which seem to match up quite nicely qualitatively. Coming to the speed up on GPUs, which we recently tried. So the corresponding publication has just been accepted. There is, so if we, here you can see the results, runtimes in wall clock for two different mesh densities. And here there's a finer graph showing that. So for small meshes, you get an overhead if you JIT compile it, if you're using CUDA. But then for larger meshes, and you typically have them for any relevant examples or any structural examples that you want to compute, then it really starts to pay off. Then this first call, the JIT time completely evaporates. So it's some below here. Doesn't play a role anymore, and you get a speed up in the cases that we computed so far of around 4 to 5. So let me wrap up my talk. So external operators plus JAGs are, sorry, that was one click too quick, are really nice for us. In order to get any constitutive models that we want in FEniCS, and that rather rapidly, because we can circumvent these tedious tensor derivations when using AD. Nevertheless, AD just works well if we use this co-rotated intermediate configuration, which we do, and then we validated our approach here for two different material classes using the same pattern essentially. Then only the constitutive law is different. Yeah. Next steps that we want to tackle is to get damage in there in both models actually. And also work more towards multiphysics, so two-way coupling of crystallinity effects, thermal and hygrothermal effects, and so on. So, thank you very much for your attention.
Thank you. So, we have time for one or two questions, maybe. Andre?
Yeah, thank you very much for this nice presentation and for interest in our work.
Yeah, thank you for providing the package.
When you explored the performance on GPU, so did you solve just a local problem, or you managed to couple the global one with the local one?
So there's no multi-scale problem in there, or what do you mean?
Yeah, well, did you have any issues regarding how you translated the values of your constitutive model from GPU back on CPU?
So it was a kind of tedious process. So it took Tianqing a while to figure that out. So the last status that I have from him is that it works nicely now. So we haven't tried it on a different example yet. Yeah. But that's everything I can say at the moment. So if
it's very interesting, the whole community struggles actually to do that.
Yeah. Okay. Yeah. So there is some repo available. However, I'm not sure if the CUDA coupling is in there. Then anyway, contact Tianqing. So I can forward you the contact. He's on our webpage as well. So in order to have a chat.
Thanks a lot to the speaker. We can stop here, I think.